When a simple pendulum is swinging from left to right, its velocity actually changes, which means that it is switching from kinetic energy to potential energy. As it moves to the extreme position, the velocity of a simple pendulum decreases, and at the extreme position, it becomes zero. Projection just means the shadow of this particular vector. So where it is lying on the x-axis. Simply simple harmonic motion will have the kinetic energy and potential energy depicted in such a manner. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing some things about oscillations. So let's get back into the chapter and see what oscillation holds for us. I never knew. So the first thing we have to learn today is spring pendulum, or more precisely, what is the time period of a spring pendulum. So we are going to derive that particular law from the motion of, or simply from the equation of simple harmonic motion, which states that F is directly proportional to negative x, that is, F is proportional to the displacement but in the opposite direction. Here we can write it as F is equal to negative kx. But we already know that F is equal to ma. So F is equal to ma, which means that ma is equal to negative kx, or simply a is equal to negative k by m into x. But we already know that k by m is omega square. So k by m is equal to omega square. So we can again substitute that, which means, again we know that k by m is omega squared from the previous equation. But the important thing is that the equation for acceleration, that is, the equation for acceleration a is equal to omega square minus omega square x. So these two equations are very similar, right? One is omega square x, one is k by m into x, which means that these are comparable equations. In the term of omega square, we have k by m. So, which means that, therefore, this spring pendulum executes simple harmonic motion, or simply simple harmonic oscillations. So again, up to this point, two things are clear. One thing is that this particular equation will give you the acceleration of the spring pendulum, and since it is of the form negative omega square x, it means that the spring pendulum is executing simple harmonic oscillations. And again, here it is mentioned x is equal to a, which is the amplitude, that is, a is the maximum displacement attainable by that particular simple pendulum. And here also we have negative a, again that is in the negative direction, and you have the mean position where x is equal to 0. You have already performed this experiment in your first PUC. If not, you are going to perform this particular experiment in your first PUC experimental labs. So again, so we proved that this is performing, or this is simply having SHM, or we can say that omega will be equal to, omega is angular frequency or angular velocity, which is equal to root of k by m, right? So we have omega is equal to root of k by m. Now the derivation is not complete yet. These are preliminary assumptions which you already know. Now, what we really need to find out is the time period of the spring pendulum. So we do know that time period is given by the equation 2 pi by omega. So time period is given by the equation 2 pi by omega, and we do know that omega is nothing but frequency, and again we can write it as 2 pi divided by root of k divided by root of m. I can write root k by m as root k divided by root m. So when it goes to the numerator, this particular equation can be written down as 2 pi into root of m divided by k. So here we have the equation for the time period of a spring pendulum given by t is equal to 2 pi root of m divided by k. So again, this small derivation will give you the time period of a spring pendulum. Now similarly, we can also find out what is the time period of a simple pendulum. The only thing you have to do is that know how a simple pendulum actually works. So again, a simple pendulum is just an apparatus where a mass which is hang from a certain height using a string. So a string which is carrying a mass, let's say m is the mass of the ball and L is the length of the string. So let's say L is the length of the string, then this particular arrangement is known as a simple pendulum. So again, how does a simple pendulum swing? It swings to and fro. That is, to the extreme positions it will oscillate. So this will be the mean position. Let's assume that, okay, this is the extreme position. Then we can say that, okay, it will execute simple harmonic oscillations. So now imagine that while this particular simple pendulum is swinging, I froze it in midair. So in this particular condition, I'm going to analyze a few things. The first thing I'm going to do is that I'm going to find out what are all the forces that is acting on this particular simple pendulum. So again, I know that since it is a mass hanging from a certain height, there will always be gravitational force which is pulling down on this particular mass, which means that gravitational force will be acting straight down. So I can call this as mg because the mass m is pulled by the gravity, that is g. So we have mg. Now one more thing if you note here is that this is at a particular angle from this particular bob. So again, the next force that is coming into play is the tensional force that is on this particular string. That is, since gravity is pulling down on that particular string, the string has a force which is acting in the opposite direction as a consequence of Newton's third law of motion. So I can just simply say that there is a force on this particular string that is indicated by the letter T, that is known as tensional force. So the only problem here is that these two vectors do cancel each other out, but the only problem is that they are at a particular angle from each other. And whenever we see one particular vector which is at a particular angle, we have to resolve that particular vector. So if the angle between them is theta, then I can say that, okay, this will be our cos theta and this will be our sin theta. So just like that, I can resolve these also into its perpendicular and horizontal components, which means that, again, so here I'm going to resolve this into the two components. So one will be the perpendicular component and one will be the horizontal component. So which is the perpendicular and which is the horizontal component in this particular figure? So don't worry, since this is theta, this angle will also be theta, which means that this is the horizontal component and this is the vertical component, which means that if I resolve mg, here it will be mg cos theta and here it will be mg sin theta. So we have T is equal to mg cos theta because it is acting exactly opposite to each other. And here one force, remember in the previous session, one force that is responsible for slowing down or changing the velocity of this particular simple pendulum, a force which was directed in the opposite direction of the displacement. That is this particular component, that is mg sin theta. So again, since the figure is complete now, I'm going to write down all the forces acting here. So T is equal to, that is this tensional force is equal to mg cos theta, which will cancel each other out. And the remaining net force, that is the net force that is in effect right now, is only one force which is leaving outside all the other forces, and that is mg sin theta. So it is mg sin theta. And since the force acting will be in the opposite direction of the displacement, we have to put a negative sign here. So we can say that net force acting is minus mg sine theta. And here I am taking the assumption that this angle, that is the pendulum that is swinging, the angle that made with the mean position is actually really small, which means that sine theta can be approximated to theta. So I can just simply write it as minus mg theta. Okay, so F net, that is net force, will be equal to minus mg theta. So again, why did I write like this? Because I want an equation in terms of theta. So theta, again, if you remember the first chapter, we have learned that theta is nothing but angular displacement. So angular displacement is theta, or simply theta is equal to arc length by radius, or simply here in this particular case, it is this distance divided by this length. So again, I told you it is of L length, and here the displacement we usually take it as x. So here also I'm taking it as x. So we can say that arc length, which is nothing but the displacement from the mean position to this particular point, that is taken as x, divided by the radius. Here in this particular case, it is the length of the simple pendulum, which is taken as L. So we can take it as x by L. So substituting here, I can simply write it as net force will be equal to minus mg. Instead of theta, we have x divided by L. Right. So this is the equation for net force that is acting on this particular simple pendulum. But our objective is not to find the net force, but rather the time period of this particular simple pendulum. So in order to find out the time period of the simple pendulum, we know that F is equal to ma. So F is equal to ma, which is equal to minus mg x divided by L. So m and m get cancelled. A is equal to, I'm taking this g by L common, so minus x g divided by L. So again, if you look here closely, you see that it is minus g by L into x. That is, A is equal to minus g by L into x, which is again of the form A is equal to minus omega square x. Right. So therefore, the simple pendulum is again executing SHM. That is, the simple pendulum is now executing a simple harmonic motion because the acceleration is of the form negative omega square x, where omega square is equal to g by L, or simply omega is equal to root of g by L. Right. So again, if I substitute here, I can get the equation as, I'll write it here. So again, if I substitute just like in the previous case, I can write this particular equation in the form of a time period. That is, time period is equal to 2 pi divided by angular frequency omega. So again, it can be written down as 2 pi divided by, instead of omega, you have root g divided by root L. Again, if it goes to the numerator, it becomes ulta. So T is equal to 2 pi root of L divided by G. This is where you get the equation of a simple pendulum actually from. So you have the equation of a spring pendulum and you have an equation for simple pendulum as well. So now, since you have the equations for the spring and simple pendulum, let's see what is the energy equation for these particular pendulums. That is, when a simple pendulum is swinging from left to right, its velocity actually changes, which means that it is switching from kinetic energy to potential energy, right? In the mean position, velocity is minimum, which means it is at rest, which means the potential energy, that is in the mechanical energy of a system, potential energy term is maximum. So what happens with the energy of a simple pendulum? So we know that as it moves to the extreme position, the velocity of a simple pendulum decreases, and at the extreme position, it becomes zero, which means that the velocity gradually decreases, which means the kinetic energy of that pendulum gradually decreases and reaches a minimum value, and then As it comes back, the kinetic energy increases, and at the very mean position, the kinetic energy reaches the maximum value it can attain, and again the process repeats itself. So according to mechanical energy, the total energy of a system is nothing but kinetic energy plus potential energy. So again, if kinetic energy is decreasing, it means that potential energy should be increasing. So as it goes to the extreme position, kinetic energy decreases, potential energy becomes maximum. And again, as it comes back, potential energy decreases, kinetic energy becomes maximum. And this process repeats on itself until air resistance gradually makes the pendulum stop. So there is an exchange of energies that is happening in this particular case of a pendulum oscillating. Not so simple, but a lot of complex principles are lying behind the oscillation of a simple pendulum. So before getting into the figures or anything else, let's write down the equations for this particular energy. So first we'll start with potential energy, which is indicated by the letter U. So we have potential energy which is given by half kx square, which we already learned in the previous chapters. So half kx square will give you the potential energy of a system, and then kinetic energy is given by, that is, Ke. Usually it is indicated by T, but again, since your textbook does not teach you that right now, I'm just going to use Ke. So Ke is given by the equation half mv square. So again, this much is the equation, but we know that x is the displacement term here, and we already have an equation for displacement that is given by x is equal to a cos omega t plus phi, which means that here potential energy U will be equal to half into k into a square cos square omega t plus phi, right? So if you square x square, it will be a square cos square omega t plus phi, and you already have half k here. So this will be the equation for the potential energy of a simple pendulum, and for kinetic energy we can write it down as half m. Instead of v square, we have an equation in for v, that is velocity, that is nothing but omega square into a square minus x square. So if you remember that particular equation, you can just substitute that particular equation and you have an equation in terms of energy also, that is in terms of kinetic energy also, which is given by half m omega square a square minus x square. Now again, the equation is not just over yet. If you assume that, okay, we are talking about the case of a pendulum, let's say a spring pendulum, then I can clearly say that this particular equation, that is omega square was written as k by m, right? Which means that omega square into m is equal to k. Why did I just write it down? Because again, there is an m and omega square here, which means I can club these together and write it as k. So I can write it as ke is equal to half, instead of m omega square, we have k into a square minus x square. So you have two different equations for kinetic energy. So you have potential energy here and kinetic energy here. Both might seem similar because again, in the same system, energy is being exchanged with each other. Now again, before discussing the energy graphs, that is how it is increasing and decreasing, you also have to know what is the total energy of the system. So total energy of a system, or simply mechanical energy, is nothing but Ke plus U. That is kinetic energy plus potential energy. So Ke is given by half mv square plus half kx square. Again, substituting for the previous values, we can write it down as half into k into a square minus x square plus half into k into x square. So again, if I open the bracket, I can write it down as half k a square minus half kx square plus half kx square. So again, there is minus half kx square plus half kx square. So both gets cancelled and the only thing remaining is half ka square. So you have the total energy of the system also given by the equation half ka square, where a is the amplitude of that particular SHM. And one more thing is that this particular total energy will be always a constant value. So that is all about energy equations of a simple pendulum. Now we can dive right into the energy graphs. So how will the energy graphs actually look like? So these are the graphs that represent the kinetic and potential energy of a simple pendulum, or simply we can say that, so any particle which is executing a simple harmonic oscillation or simply simple harmonic motion will have the kinetic energy and potential energy depicted in such a manner. If you're taking kinetic energy versus potential energy, then we can say that kinetic energy will be a sinusoidal graph which is starting from the origin and it is propagating as such. If you start with potential energy, that is, the potential energy is a cosinusoidal graph or simply a cosine graph which is starting from the extreme position and it will carry on like this. Similarly, if you are taking in the case of a simple pendulum, then we can say that the total energy will always remain a constant. So that is what is shown here. And then we have what is known as kinetic energy of a simple pendulum, which again, it starts from the lowest point possible, that is from the extreme position, and it reaches a maximum value at the mean position, and then again it drops down to a minimum value, that is it is swinging from left to right. As it is executing that particular motion, the potential energy of the system will start from a maximum value and it decreases to 0 at the mean position, and then again it increases. So that is how potential and kinetic energy exchanges between a system is shown here. Remember, this is the mean position, this is the extreme position, that is either left or right. So again, that is all about energy graphs of an SHM. Now, the last topic in this particular chapter is the relation between circular motion and an SHM. So you know that if a particle is executing a circular maneuver or a circular motion, it is a periodic motion rather than an SHM. But is there any relation between an SHM and a periodic motion such as a circular motion like this? So our objective is to find a relation between circular motion and a particle which is executing an SHM or simple harmonic motion. So we can say that if a particle is executing a circular motion at any given point of time, then I can draw a radial vector like this indicating the position of that particular particle. So let's say that from this particular x-axis, it is at an angle of omega t, right? It is at an angle of omega t. And after some time, we can say that the particle is continuing to move forward, that after some time, the particle reaches this particular position, and I'm saying that from this particular position, that is from here to here, the angle is phi. So initially the angle was omega t and after that it was phi. So the net angle now is omega t plus phi. But at each point in time, I'm only taking the positions. So like this, I can take any individual positions along this particular circular path. And depending on that particular circular path, I can get the position of that particular particle which is executing a circular maneuver. The point here is that even though the particle is going around in a circular path, if I take the projections of that particular particle, what is projection? Projection just means the shadow of this particular vector. So where it is lying on the x-axis. So I am taking the projection, not on the y-axis, just on the x-axis. So the projections or the shadows of the particle which is executing a circular motion is taken on the x-axis. Then I can say that initially it was here. So initially it was here. After some time it is here. After some time it is here. Now if I keep on measuring it, after some time it will reach here, which means the projection will be here. And after some time it will reach here, which means the projection will be here. And after some time it will reach here, which means the projection will be here. Now when it goes down, or when it is executing or completing the circular motion, when it reaches here, what will happen? Again the projection will be here only. And when it is here, again the projection will be here. Which means that on the x-axis, if I just focus on the x-axis, then I can say that even though the particle is executing a circular motion, the net effect of that is in the x-axis given as something which is moving to the left to the right. It is moving from left to right. So even though the particle is going like this, if I take the projection, the projections are going like this. That is back and forth. Or another way of saying that is to and fro. So the particles are moving to and fro. So that particular thing is the relation between circular motion and an SHM. So mathematically we can just write it down very quickly and that finishes up the chapter. So we know that x is equal to a cos omega t plus phi, which means that if I take the derivative, that is dx divided by dt, I'll get again a omega, there will be a negative sign, sine omega t plus phi, and that is nothing but the velocity of this particular particle which is executing a circular maneuver. Or simply we can say that now you know what is the relation between oscillatory motion and the circular motion. So again we have this particular relation, and if I take the square of this, then I can say that, or simply the next derivative, that is acceleration, I can simply say that a is equal to dv by dt, again which can be written as a omega square cos omega t plus phi. Now if I take this a cos omega t plus phi, that is nothing but x, a cos omega t plus phi. So I can write it down as negative omega square x, which is nothing but the equation for acceleration, which means here also the particle is executing a simple harmonic motion. The only condition is that it should be a uniform circular motion. So here again, since we got this particular condition from that particular result, I can say that since the projection projections on the x-axis is of such form, the particle in uniform circular motion is executing SHM. So it is also having simple harmonic motion. So that is all about oscillations for now. I'll see you all very soon with a new chapter. Until then, thank you.